we're happy to have Alexander Clifton speaking today about an exponential bound for exponential Diff sequences.
All right, thank you, Sam. So my talk is called an exponential bound for exponential Diff sequences. And I think we know what maybe all but one of these words mean, and I'll explain what Diff sequences are in a little bit. But first, so this work counts as arithmetic Ramsey theory. And one of the core slogans you'll see in Ramsey theory is that complete randomness is impossible. Another slogan I like is that if you divide, or there's a central question of Ramsey theory, is if you divide a whole into parts, traditionally the parts are colors, is one of the parts guaranteed to retain some special structure. So you're used to maybe coloring edges of a graph and wondering if you get like a monochromatic subgraph that's isomorphic to some fixed H. Well, today we're not going to color any graphs. Instead, we're going to just color integers. So first, I'll start with a big, bold claim that the positive integers contain arbitrarily long arithmetic progressions. Now, if you split them into two parts or two colors, will this still be true? Will you have an arbitrarily long monochromatic arithmetic progression? Or what if you have 3 parts or 4 parts or any finite number of parts? So this is the content of van der Waerden's theorem, which is almost 100 years old now. So this is, the answer to this question is yes. If you color the natural numbers with any finite number of colors, then you will get arbitrarily long monochromatic arithmetic progressions. This is phrased a little more quantitatively. There is some n, but if I just color the first n, I am going to get a monochromatic KAP. And you might wonder what the smallest such n is. So this is the definition of a van der Waerden number. It's the smallest n such that any R coloring of the first n positive integers includes a monochromatic KAP. So the content of van der Waerden's theorem is just that van der Waerden numbers exist. And in practice, we know a few infinite trivial families. We know a few small cases. That's all we know exactly. There are some very interesting bounds. So there's this power tower that's maybe like 5 layers for upper bound. Presumably that's not tight, but interesting problem to look into. If you were trying to show something exactly, you would do kind of what you do for any sort of Ramsey theory or just generally extremal problem. To get the lower bound, we just need to show that there is some coloring of the first WRK minus 1 that misses a monochromatic KAP. And then for the upper bound, you show that if you have up to WRK, no matter how you color it, you are going to get a monochromatic KAP. So just for fun, let's try to show that W23 is 9. So 9 is the smallest number such that if I color the first n numbers red and blue, I get either a red 3AP or a blue 3AP, no matter how hard I try not to. So 8 is not enough. So you see here, if 1, 4, 5, and 8 are red, 2, 3, 6, and 7 are blue, you can verify there is no red 3AP, there is no blue 3AP. Now we'll show that you can't do that for 9. So there's 2 possibilities. I could either make 4 and 6 the same color, or I can make 4 and 6 different colors. So first case, assume 4 and 6 are the same color. Well, let me just hide the names of annotators. Okay, so if you're trying to avoid a red 3AP now, then you have to make sure 5 is blue, otherwise you have 4, 5, 6. You have to make 8 blue because 4, 6, 8, and you have to make 2 blue because of 2, 4, 6. So in our best efforts to avoid this red 3AP, you notice now we've gotten 2, 5, 8 as a blue 3AP. So if we have any hope of this working, we're going to have to make 4 and 6 different colors. So let's make 6 blue. Let's make 4 red. Because of the symmetry without loss of generality, I can make 5 red as well. Doesn't matter. And now we get to play Sudoku. So what I mean by that is that each action is going to be fixed by the previous decisions. So we don't want 3, 4, 5 to be red, so 3 is blue. We don't want 3, 6, 9 to be blue, so 9 is red. We don't want 1, 5, 9 to be red, so 1 is blue. We don't want 1, 2, 3 to be blue, so 2 is red. And now we don't want 2, 5, 8 to be red, so 8 is blue. And now look at 7. So if 7 is blue, we get 6, 7, 8 monochromatic. If 7 is red, we get 5, 7, 9 monochromatic. So we're stuck. So in our best efforts to avoid a monochromatic 3AP, we got one anyway. So that shows that this van der Waerden number is equal to 9. And instead of arithmetic progressions, you might wonder, well, what other structures might I be able to make these van der Waerden type theorems for? So what structures are going to be retained within one color? So here's a notion of a diff sequence due to Bruce Landman and Aaron Robertson. So it's given an infinite set that you fix. It's an increasing sequence, a finite increasing sequence, where all the consecutive gaps, A2 minus A1, A3 minus A2, et cetera, are in your set. So just an example here, if we have D as the powers of 2, then this is a D diff sequence of length 6. So 11 minus 3 is the power of 2, 15 minus 11 is the power of 2, et cetera. So this is 5 gaps, 6 numbers. So the length is the number of numbers. So the question is, can you make a van der Waerden theorem for diff sequences? So here, we don't care if the differences are the same as each other. We just care if they're in our fixed set. So whether you can make a van der Waerden type theorem or not for R colors is this notion of R accessibility. So we say a set D is R accessible if there's some N such that no matter how I color the first N, I am going to get a monochromatic length K diff sequence. So just to make sure everybody's okay with this definition, let's do an example. So if you have the set of even numbers, I claim that this is R accessible for any number of colors. And to see why, we're just going to show that a coloring of the natural numbers contains arbitrarily long D diff sequences. We only have a finite number of colors. So one of your colors has infinitely many elements, either infinitely many odd or infinitely many even. But the point is you have infinitely many numbers that are the same parity and the same color. So if you take the pairwise differences between them, they're all even, they're all in your set D, so you can get an arbitrarily long D diff sequence in that color. Now, let's see an example where it's not R accessible. So the set of odds is not R accessible, even if R is as low as 2. So let's try 2 colors. I'm going to say all my evens are red, all my odds are blue. If you take a monochromatic D diff sequence, it's all numbers of the same parity. So even if you wanted to have 2 of them, the gap between them would be even and wouldn't be in your set D. So even with just 2 colors, you can't even get a D diff sequence longer than length 1. And if you can't do it for 2 colors, you can't do it for 3 colors either, because for 3 colors, what I could just do is say the third color is never used and it just defaults to what I did with the first 2 colors. And similarly for any greater number of colors. So if you're not 2 accessible, you're not going to be R accessible for any larger number of colors either. So now my talk is about exponential diff sequences. So let's consider the set of powers of 2. So this is known to be 2 accessible. And what we'd like to do is we'd like to find this analog of the van der Waerden numbers. So what is the smallest number such that if I color the first n positive integers, with 2 colors, I'm guaranteed to get a monochromatic powers of 2 diff sequence of length K. So Landman and Robertson explored this question. So for the lower bound, all you need is 1 coloring that avoids these things. So they had this sort of periodic coloring mod 8, which is where this 8K is coming from. So they got a linear lower bound and they have this exponential upper bound. So with my RAU collaborators, we improved the lower bound to quadratic, but that's still a pretty big gap to have this polynomial lower bound and an exponential upper bound. But if you've read the title of the talk, you might see where this is going. So the result I'm going to talk about today is I now have an exponential lower bound. There is still a considerable gap because if you notice my lower bound, the exponent's on the order of square root of K, whereas the upper bound, the exponent is linear. So a pretty big gap still. However, in practice, the computations I've done for K up to 12 make it look like the lower bound is pretty tight. It's probably what's written there, maybe +2 or something, plus a constant. So it would appear that's the case, but then again, it's only known up to 12. So maybe it's not actually as tight as it looks. So before I talk about why the lower bound is true, let's refresh the upper bound. So here to show that, we're trying to show that if you color 1 up through 2 to the K-1, you're guaranteed to have a monochromatic powers of 2 diff sequence of length K. So the base case is 1, not very interesting. I color 1, that's my D diff sequence of length 1. So for the induction, suppose that I have within my first 2 to the K-1, I have some red D diff sequence in increasing order, that's A1, A2 up through AK. So if AK plus 1 was also red, I could just tack it on to the end of my sequence and get a red D diff sequence of length k plus 1. If AK plus 2 was also red, I could also tack that on to the end of my sequence and get a red D diff sequence of length k plus 1. Similarly, for AK plus 4, AK plus 8, AK plus any power of 2. So if I have AK plus a power of 2 also red, I can add it on and increase my sequence from length k to k plus 1. If I want to stop that from happening, then I have to make it so that AK plus any power of 2 is the other color, blue. But this would mean AK plus 1 is blue, AK plus 2 is blue, all the way up to AK plus 2 to the k is blue. And you notice that sequence, those elements themselves form a D diff sequence because all the gaps between consecutive terms are powers of 2. So in our efforts to avoid a red D diff sequence of length k plus 1, we would have forced the existence of this blue D diff sequence of length k plus 1. And the largest term in that sequence is AK plus 2 to the k, which is at most, whatever AK was at most 2 to the k minus 1 plus 2 to the k. So we get that, yes, we would be forced to have within our first 2 to the k plus 1 minus 1 numbers, a monochromatic D diff sequence of length k plus 1. So the induction is complete. And in the rest of the time, I'll talk about the lower bound. So here I ditch red and blue. We just use color 1 and color 0. So what's going on with this table? So the first row is just going to be a periodic coloring mod 2. So 1 is color 1, 0 is color 2, 3 is color 1, 4 is color 2. I say color 2, I mean color 0. And then you repeat like that. So you're coloring according to parity. And why is this the thing you'd want to do? Well, we're trying to avoid gaps that are powers of 2. And at the very least, well, this makes it so X and X plus 1 are different colors. So we avoid gaps of size 1. Next row, here's a periodic coloring mod 4, 1, 0, 0, 1. So that means 1 is color 1, 2 and 3 are color 0, 4 is color 1, and then you repeat. So 5 is color 1, 6 and 7 are color 0, etc. Where is this coloring coming from? Well, the 1, 0, the first half is the previous row, and the 0, 1 is like the complement of that. So actually, there's something called, I think, the through-Morse sequence. So each row of this is like the first 2 to the n bits of the through-Morse sequence. So the good thing about this is by construction, it makes it so that X and X plus 2 are always different colors. So we've at least avoided gaps of size 2 within a monochromatic sequence. That alone wouldn't be super important, but the good thing about this coloring is it also limits the number of gaps of size 1. So if I keep this block pattern going, no matter how long a monochromatic sequence I take within this coloring, I am still going to have only one gap of size 1 at most. So there's a constant upper bound on the number of gaps of size 1. And let's take it a row further. We have this repeating block 1, 0, 0, 1, 0, 1, 1, 0. So the 1, 0, 0, 1, again, I copied the previous row. 0, 1, 1, 0, that's just the complement. I take the 1s, replace them with 0s, take the 0s, replace them with 1s. So this makes it so X and X plus 4 are always different colors. So I avoid gaps of size 4, but I also, turns out I have a limit on how many gaps of size 1 and 2 I have. So the key to showing the lower bound here is to quantify this behavior in the third column. So we can take this table and continue it. So PT, what you do is you get it by taking PT minus 1 as the first half and taking the complement of PT minus 1 as the second half. So this table is P1, P2, P3, but you can keep going. We're going to say a short gap is any gap less than 2 to the T minus 1, and a long gap is any gap that's at least 2 to the T. And if you wonder what happened to gaps of size exactly 2 to the T minus 1, well, we don't care because, as you can see from the middle column of our table, those don't happen anyway. So the lemma here, it quantifies upper bound on the number of short gaps using PT. So if I've used PT and I'm taking some D diff sequence with respect to that coloring, I'm actually going to have at most T squared minus T over 2 short gaps. And I don't think I'll get into why that's true, but I will say that it's a little more specific than this. Really what it is it's at most 1 gap of size 1, at most 2 gaps of size 2, at most 3 gaps of size 4, at most 4 gaps of size 8, et cetera. And if you add them up, you get something that looks like T choose 2, which is where this total is coming from. So if you have an upper bound on the number of short gaps, you have a lower bound on the number of long gaps. So AK minus A1, the difference between the last term and the first term in my diff sequence, is just the sum of the gap sizes. Well, I can bound the sum of the gap sizes below by the sum of the long gap sizes. So where does this bound come from? 2 to the t is the lower bound on the length of a long gap. And this term, k minus 1 minus t squared minus t over 2, is the lower bound on the number of long gaps. So the product is a lower bound on the total length of the long gaps, and that serves as a lower bound for the total length of all the gaps. So if you look at this, what you'll see is you get a different linear lower bound for each choice of t. So it may seem like I lied to you because here there is an exponential, but it's an exponential in terms of t, and I promised an exponential in terms of k. However, what you can do is you can choose t in terms of k, and if you do that, you do get the asymptotic I claimed earlier. So you might wonder why exponential Diffsequences, why I'm only talking about powers of 2. Well, it turns out it's not an interesting question for powers of 3, 4, etc., because the powers of r, they're all 1 mod r minus 1. So you can just use some sort of periodic coloring mod r minus 1 to show that it wouldn't be too accessible anyway. However, if you still want some sort of exponential growth, it might be interesting to consider some number that's not an integer and then just take powers of that, but then do either floor or ceiling so we can still have roughly the same growth, but not have to worry about automatically not being accessible or anything. I haven't done too much on that question. I've messed around a little bit with like pi and e, and I'm not sure what's happening. This last question here. So of course, there's nothing special about taking powers of r. You can take any d that you want. And there's some examples of d where the numbers you get, the analogs of these van der Waals numbers are polynomial in terms of k. Here it's exponential in terms of k. So one thing I'm just wondering is like, what is the general behavior you can get? And whether it's possible to still be accessible, so still be finite, but grow faster than exponential. And I don't know. So that's maybe a thing to think about. All right. Thanks, everyone.
Cool. Let's briefly thank Alexander. And we're a little over time, so are there any quick questions for Alexander? Just to perhaps comment, Alexander. So is it correct that you can, if you have d with odd integers, you can just like throw them away and that doesn't change the fact that you're are accessible or not? Is that true or false?
Wait, I think I maybe don't understand.
So if we did this periodic coloring, is it true or not that like if I have an odd integer, I can just throw it away from d and that doesn't change whether it's r accessible or not? Is that true or false?
It might not change the accessibility because, okay, so this particular proof, the reason it worked is that within the set D, there's an infinitely long D diff sequence, right? Because 4 minus 2, 8 minus 4. So if I throw out 1, I can just repeat that same upper bound argument and just say it's ak plus 2, ak plus 4, ak plus 8. It might change what the upper bound is, but you're right. In that case, you can throw away the 1 and you'd still have that the powers of 2 without 1 are still accessible for at least for 2 colors.
Any other last questions? If not, let's thank Alexander again.